Hello, welcome to Essentials of Computer Architecture and Organization. And this is our last lecture covering the material in Coomer. So thank you very much for a good course. And so what we're going to be talking about for this last lecture is hardware modularity, I'm sorry. And so we will be talking about that and thinking in terms of boards and replication. And so in terms of modularity, we can be thinking this from the software perspective or from the hardware perspective. So for software, it can be easy. You just build parametric functions, but for hardware, it can be difficult and you must replicate hardware units. And so there's a trade that needs to be considered. In terms of hardware design, there's the desire that you want to build a series of products, include a ranging of sizes, and avoid designing each from scratch. So the solution is to design a basic building block, and you can replicate the block as necessary and arrange to activate the pieces as needed. So a little bit more of a modular type of a design. And Coomer has thought about this some, and we have some custom type of projects that we have done, but Coomer has a lab example, what he calls a rebooter. And so that's the example that you can read in more detail about in the textbook. So it's a specialized, it's a homemade hardware mechanism. It provides power to each back end. It receive commands from the control software. It can power cycles the specified back end. So here is, say, what that could look like. So all back end computers are numbered, and the control software issues the commands to reboot. The command is converted to binary value and set to the rebooter, and the rebooter power cycle specific the specified backend. So which one do you need to reboot? And so here's gives you some control logic and a way of doing that. So a question that Coomer would have us consider is, how big should the rebooter be? So we say we start with 8 machines, and it's grown to over 100. And just thinking and having a mental exercise of how that might look. So if we want to build a rebooter that is too small, it would be insufficient. But if we build one that's too large, that would be wasteful. So those are the traits. So it depends on the type of scenario, the type of application. We're thinking of the school, so say school enrollment. And what if we do not know in advance how large the class or the lab would be? So the hardware engineer would be designing products that face the same kind of a dilemma. So we're thinking of an academic type of problem, but it's similar to what would be happening in industry when they're actually doing some design. So in order to achieve hardware modularity, we want to design a basic type of rebooter hardware and then replicate it as needed. So that's how we can be extensible based on the need at hand. So one possible design is to arrange a basic module that controls 16 devices. So we'll use that as a basis. And so we can be thinking in terms of binary. So if we assume an 8-bit binary input, so that would give us up to 256 backends, the lower order 4 bits of the binary input are used to select one of 16 devices, and the high order bits of the binary are used to select a specific module. So each module is given a unique ID between 0 and 15, and a given module only responds if the high order bit of the input match is the corresponding ID. So the design allows the same binary input to be passed to all modules in parallel. So here's an illustration of what that could look like. So say if we have 4 modules that allow 64 backends, and so here we would have these 4 ID modules. And so first you'd have to locate this first part of the address, and then you can get more specific to the next level, going to a particular device. So in each of these, this is something that can be extensible. And so hardware designers use this modular approach to build a series of products with various sizes. So we would then consider approaches for assigning an ID to a module. So one technique would be using a set of switches that would work. Switches on a module are set to a specific ID. A comparator circuit then compares the ID to see if that's right. So that's one, it's a possibility, but if a module fails, it can't be replaced. So of course, you must be careful to ensure that each module has a unique ID. So pluses and minuses there. So here would be a way of considering this in terms of interpreting the input. The same inputs by input bits are sent to all the modules. All modules operate in parallel to check the module identification bits, and only one module will match the identification. And then you go to the next step. So in summary, a hardware design is expensive and usually unique. The technique used for modularization is replication of a basic building block. Data is sent to all the modules in parallel, and each module is configured to respond to a specific set of inputs. The typical scheme is to use the high order bits of the input to select a module. So the first part of an address, if you will, and the low order bits to specify a function on that module, say a more specific type of aspect of and getting to a particular module, particular address. All right, well, thank you very much. We'll finish this up, and I hope that you enjoy this class.